So so far we have defined two abstract constructs. One of them is an ordered set. It's a set on which an order has been defined. And secondly, we just now defined a field, right? That is a set on which two operations, addition and multiplication, are defined, which satisfies certain natural properties, right? Now what we need to do is essentially combine these two to define what is called an ordered field. Okay, so an ordered field, as the name suggests, is a field which is also an ordered set. An ordered field is a field F which is also an ordered set. But so note that all the properties that we have for a field involve only addition, multiplication, or a combination between the two. All the properties we have on an ordered set are to deal with simply the ordering itself, right? The fact that if x is less than y and y is less than z, then x must be less than z, right? You also need, it turns out, a couple of properties that link the ordering to the properties of addition and multiplication that have been defined on the field, right? So I need two more axioms on top of the definition of a field and that of an ordered set to define an ordered field. And these two properties are the following: for all x, y, z in F, it is true that y less than z implies x plus y less than x plus z. Okay, so this is a kind of natural property that if y is less than z, I am quote unquote allowed to add x on both sides and the inequality still holds, right? So you are allowed to add the same element to both sides of the inequality and it still holds, right? That's the first property. So remember, note that this is something that links the ordering property to the addition property, right? The ordering property from the ordered set to the addition property from the field, right? Now also we need something that relates the ordering to multiplication. For all x, y in F, x greater than 0, y greater than 0 implies that xy is greater than 0. Okay, now this is again another very interesting property. Remember, the 0 is an artifact of the field. It is the additive identity of the field, right? But once you have an order, it makes sense to ask whether any element x or y is greater than 0 or less than 0, right? So I can in words say x greater than 0, y greater than 0. I could say that x and y are quote unquote positive, right? Again, what is positive? Again, this is just intuitive language, but an element would be positive if it is greater than 0, right? And from the definition of a field and that of an ordered set, we know that any element must either be 0 or it should be greater than 0 or it should be less than 0, right? So for all non-zero elements in an ordered field, I can talk about them as being positive or negative depending on how they compare with 0, right? So the second property that I've written here tells you that if I take two positive elements, then their multiplication is also a positive element. Okay, so an ordered field is a field which is also an ordered set that satisfies these two additional properties. All right, so that is the formal definition of an ordered field. Let me of course give some examples. The natural first example to think of is of course Q and R. These are ordered fields. As R I have not formally defined. I'm going to tell you that R is an ordered field in the next slide, but since we have some prior familiarity with the set of reals, I'm just going to write that down here anyway. Okay. The other, interestingly, is that C, the set of complex numbers, is not an ordered field. So this is something you should think about. I'm going to leave this as an exercise a little later in the video, because one of the properties we will prove will help you to prove this, but this is something you can already pause and think about right now. Right? We have already defined the complex numbers. Okay, so among complex numbers, you already have a well-defined notion of addition and multiplication, right? Use those well-defined notions of addition and multiplication and show that it is not possible to define an order on the complex numbers. In other words, that it is not possible to define any ordering on the complex numbers such that with the default definitions of addition and multiplication, the set of complex numbers becomes an ordered field. This is not possible. It's not hard to see, but it's going to be, if it's not already clear to you, it will be clear very shortly. Right? Another thing that is not an ordered field is finite fields. No finite fields are ordered fields. Right? If you haven't encountered finite fields before, just keep this in the back of your mind. The goal of this course is not really to study finite fields at all, so I'm not going to get into details here. But if you have in fact encountered finite fields before, it might be worth your time to just go and convince yourself that finite fields cannot possibly be ordered. So finite fields, of course, already have their addition and multiplication operations defined. All we are trying to now say is that it is not possible to define a consistent ordering on finite fields. Okay, so that's the point. So all ordered fields, a consequence of this statement is that all ordered fields are necessarily infinite, right? The number of elements in the set is necessarily infinity. Okay, now just as we had done before, let me write a quick lemma which summarizes some nice properties which will be nice consequences of just the definition itself. So the first property that we're going to write is that if x is greater than 0, that's equivalent to saying that minus x is less than 0. Okay, so if x is positive, its additive inverse is in fact negative. That's the first property. Second property is x greater than 0, y is less than z implies xy is less than xz. Okay, now this is again a property that we are used to using in the context of real numbers. So if I take an element which is positive, which means it is greater than 0, and you have y less than z, then I can quote unquote multiply x on both sides of this inequality and it remains valid. Okay, so that's the second property that I'm going to prove. There are many more interesting properties to be proved about ordered fields. Many of these I'm going to put as part of your first homework. All right, and the third property that I want to show is that if x is not 0, then x square must be positive. Right, and an immediate consequence of this is that 1 is necessarily positive. Remember, 1 is the multiplicative identity. And so 1 is also 1 times 1. So 1 is the square of 1. So if it is true that the square of any non-zero entry, the square of any non-zero element is positive, it follows that 1 must be positive. Right? Namely, the additive identity must be greater than the multiplicative identity must be greater than the additive identity. Right? This follows from the axioms, as we will see. Okay, so now let's go through again a quick proof. As I said, these proofs are largely 1 to 2 lines, so they are fairly straightforward. So let's look at the proof of statement 1. If x is greater than 0 is equivalent to minus x less than 0. Now this is an if and only if statement. I'll just bother proving one side and leave the other side as an exercise to you. Okay, if x is greater than 0, this implies, now remember from the first property that I have defined for the field, I'm allowed to add something on both sides of an inequality. I'm going to add the additive inverse of x. So x plus minus x is greater than 0 plus minus x, right? Which in turn tells you x plus minus x is of course 0. So 0 is therefore greater than 0 plus minus x is by definition minus x. Okay, so if x is positive, that means that minus x is negative. Again, a very similar argument will show that the opposite is also true. Okay, let's look at statement 2. Statement 2 is that of the lemma is that if x is positive and y is less than z, then xy is less than xz. Okay, so how the way I'm going to prove this is the following. If y is less than z, that means that z minus y is positive. How do I get this? I'm actually getting this by using the first property. What I've done, if you think about it, is add minus y to both sides of this inequality. If I add minus y to both sides, then in fact I will get z minus y is greater than y plus minus y, which is 0. Okay. Now that I have this, now I can apply the second property. Because z minus y is positive and x is positive, I can conclude that x times z minus y is also positive. Okay. Now I use the distributive property to argue that x times z minus x times y is positive. Okay. And then all you have to do is add xy to both sides of this inequality. Use the associative property on the left to argue that xz is greater than x times y. Okay, so this is how you would prove the second statement. To prove the third statement, let's move on to the next page. The third statement, recall, was the following. We had to prove that if x is not 0, then x square must be positive, which of course implies that the one element, the multiplicative identity, must also be positive. Okay, so how do I prove this? If x is positive, then there is nothing to prove, because it actually follows that x times x must also be positive. This is by axiom number 2 in the definition of the ordered field, right? If x is negative, remember, if x is not 0, it could only possibly be positive or negative, right? So if x is negative, then if you go back to one of the properties that we proved about the field, then we said that x square is in fact also the same as minus x times minus 6, right? But we just said that minus x is positive. So this fellow is positive, this fellow is positive, which implies that this fellow, the product of minus x and minus x, is also positive, right? So that's it. So we have proved for positive elements that the square of a positive element is positive follows from the axiom. For a negative element, that the square is positive in fact follows from this property that we have already proved in the context of a field. Okay, so this is just to give you a flavor of the kind of things that one can prove by starting with a very small but rich set of axioms, right? It is basically to illustrate that small minimal set of axioms that we involved in the definition of an ordered field lets you prove a whole bunch of consequences from those axioms. Okay, so there will be a lot more practice of this in the assignments going forward. So now that I have formally defined an ordered field, I'm now going to tell you what is R. Okay, so this is our first big result, which unfortunately we won't prove. There exists an ordered field R which satisfies the LUB property Okay, so this is how I define R. In fact, R, it turns out, is an ordered field which satisfies the LUB property. Such a construction is possible is what this theorem is saying. Moreover, R contains Q, the set of rationals, as a subfield. Okay, so I am in fact not going to I'll tell you what a subfield is in a bit. We are not going to prove this result, but Q by itself is a subfield. Sorry, Q by itself is a field, right? Is an ordered field but Q does not satisfy the LUB property, the least upper bound property. What this theorem tells you is that I can construct an ordered field R of which Q is a subset which satisfies the LUB property. In other words, I am extending Q to the set of real numbers, essentially adding a bunch of elements to Q in such a way that that extension is also an ordered field and satisfies the least upper bound property. And that extension is in fact consistent when it comes to addition and multiplication when it is restricted to the rationals. So specifically what it means to say that Q is a subfield is the following. Q being a subfield of R means that Q is a subset of R and the operations and ordering on R when restricted to Q are consistent or coincide with those on Q. Okay, so this is really the big result of this chapter, which I have only really set the stage for. We are not actually going to go into the proof, but let me summarize what it is that we have said. We have said that we have identified that Q, the set of rationals, is an ordered field. This is evident. However, it does not satisfy the least upper bound property or equivalently the greatest lower bound property. Okay, so how do I construct R? I construct R by essentially defining a bunch of elements which I will add or add to Q, right? In such a way, so those elements are, as we expect, the irrational numbers, right? So I add the irrational numbers to Q to define this extended set R, which it turns out is an ordered field, which does in fact satisfy the least upper bound property. Moreover, all the operations as well as the ordering that is defined on the the constructed superset R will in fact coincide with those on Q when they are restricted to Q. So the elements of Q are a subset of the elements of the set of rationals is a subset of the set of reals, and the operations on the reals are in such a way that they are consistent with those on the rationals. Okay, in other words, addition and multiplication within R, addition and multiplication of two rational numbers would correspond exactly to our prior understanding of how addition and subtraction between rational numbers works. Okay, so since we had defined an ordered field in this video, I thought it was good to kind of highlight the main result here. What we will not do is prove this statement formally, because proving this basically boils down to giving a rigorous a rigorous construction of the reals, which is not really the the point of this course. So those of you who are interested, I would recommend you to read chapter 1 from Rudin. So he actually does have a short description of how formally the construction of the reals is done. What we will instead do is, instead of proving this result formally, in the next week, what we are going to do is, look at various consequences that come from this result. Namely, what are some of the things that we can do in R that you cannot do in Q. Remember, one of the first things that I said about Q is that there is no solution to the equation x square is equal to 2 within the rationals, right? We will show that given that R is an extension of Q that satisfies the LUB property, there is in fact a solution to x square is equal to 2 within R, even though there isn't one in Q. So these are the kind of things that we will in fact prove in the next week, as a consequence of the fact that R is a quote-unquote superfield of Q, right? Q is a subfield of R. From that, we will be able to prove various interesting properties of R. Okay, so this basically concludes the material for this week and this video. There will be several exercises that follow.